Next is the failure behavior of isolated footings. A sufficiently thick isolated rectangular column footing may fail by flexure cracks parallel to each side close to the column, or by one-way shear cracks also at the same locations. Here, first of all, I will show here. Here is a footing. Okay, so the footing will act as a one-way slab. So movement at the spot where the column is going to connect at the foundation, there is chances that cracks appear here. Okay, so that is the flexure failure. Or there may be chances that the column punches to the foundation. Okay, so that is a shear failure. Okay, so here is a before failure. After failure, column is punched. So why the column is punched? Because the concentrically load is more than the bearing capacity of the foundation, so that is punches to the foundation. Here is a real picture. Again, so either the footing can be failed due to the flexure, or means due to movement, or due to the shear. So however, the most common failure of such a column is by punching through the relatively the slab. Means the most common phenomena of the failure of the footings, that is a punching failure. The failure occurs around the perimeter of the column by a special type of shear called the two-way or the punching shear, as shown in figure here. Okay, in this side and this side, both way shear acts simultaneously, so the column punches through the foundation. So that is a two-way shear. Due to the presence of simultaneous high vertical compressive stresses, lateral compressive stresses at top of footing, and lateral tensile stresses at the bottom of the footing, the critical section for the calculations of the strength against this type of shear failure is to be considered at d/2. What it means here? Means here is a column. Here is you are seeing dotted lines. That is distance d/2. D is the effective depth of this footing. Okay, d/2, d/2 in both ways, this way and this way. So for the analysis of this two-way shear, we will consider the location at distance d/2 from the face of the spot. That is given by as per code. Okay, d/2 at distance d/2 from face of the column, compared with these distance taken in case of one-way shear. So when one-way shear, what is one-way shear, I will also show in the critical sections for one-way and two-way shears are shown in figure 9.4. In one-way shear, the one part of the slab punches down. Okay, one part of the slab, footing slab punches down. So that is a critical section for one-way shear. And for one-way shear, we use the effective depth at a distance d. So that guidelines are given by the code. So we will use as it is as in our calculations. Simple words, I will repeat again. For two-way shear, we will calculate at distance d/2. And for one-way shear, we will calculate at a distance d. It is not common practice to provide shear reinforcement in the footings, and hence these are usually designed by sufficiently increasing the depth of the footing. Means the applied shear we entirely resist by the thickness of the footing, means by the concrete only. We do not provide in the foundation the shear reinforcement, such that the concrete shear strength alone is greater than the applied punching shear. So to confirm the one-way and two-way shear, we check that our thickness of the slab okay to resist the one-way and two-way shear. In single footings, the total and effective depth of footings is mostly governed by shear and is decided in the start of the design process. Okay, so in single footing, the total and effective depth depends upon shear, and that is decided at the start of the design of foundation. So how to calculate the shear strength of the footing? So the concrete strength against two-way shear is estimated as below. To calculate the concrete shear strength, here is three criteria. We get the strength from each criteria. the lesser of the following. So whichever the strength is lesser, we will take as the shear strength of the concrete of the footing pad. Here is some nomenclature. B naught. What is B naught? B naught is the perimeter. Okay, so this distance, this distance, this distance, this distance, which is coming in the punching. Critical section perimeter at a distance d by 2 from the column perimeter. D is the effective depth. Beta, ratio of long to short side of the column. Okay, long to short side of column, that is a beta. Alpha S, a constant, that is a constant. It is used for interior column footing, that is 40, for edge column footing, that is 30, and for corner column footing, that is 20. And lambda is a normal weight concrete, that is 1. According to ACI code 15.7, the depth of footing above the bottom reinforcement should not be less than 150 mm for footings on soil and not less than 300 mm for footings on piles. Means that is saying the effective depth nearly plus you can say 10 to 25 mm. So you can say your depth in the examples author generally given, this is the effective plus 75 mm from the center of the bars to the edge. So plus D plus concrete cover. Okay, so 150 plus, so author has decided the value 250 mm. So now I will conclude this line. So your footing depth should not be less than 250 mm. And for piles you can add again 375 mm. So in the footing piles you can say rounded to upper side, your footing or the pile cap thickness should not be less than 375 mm. The applied load causing punching shear is calculated by here in the previously how to calculate the capacity, how to calculate the applied shear. Here is the formula. Okay, the punching shear formula. Here is the applied load multiplied by area of the footing outside critical perimeter. Okay, this area means outside this critical perimeter, all the area will be included in the punching shear calculation. So B into L, that is B is the total width of the footing, length is the total length of the footing. So minus B1 into B2. B1 and B2 are B1 the perimeter means this critical in one direction, that is B1, in other direction, that is B2. Okay, here you can again see the B and L, B1 and B2. You will calculate total area B into L, subtract B1 into B2. You will get the area of this. Area effective in producing punching shear. Now design bending moment and one-way shear for isolated footings. The critical section for calculating the bending moment is considered at the face of the column. Okay, so all the slab is projecting away from the column. So the slab of the foundation is to be decided as one-way slab. Referring to figure 9.6, here you can see here that is a, you can say, the long side of the foundation. Okay, as the face of the column, the remaining length, if the in the longer side the column dimension is C1 and the shorter side the column dimension is C2. So in the longer direction, L minus C1, when you minus L minus C1, then divide by 2. Okay, so you will get this length. Okay, so you can again total length minus the C1, you will get the all length, then divide by 2, you will get this length. Okay, so similarly in this you can say in the shorter direction. Again, this is b minus c2, b minus c2 divided by 2, you will get this length. Okay, if you have the length for the and the load, that is qu. So if you have the load and the length, you can calculate the moment. For the cantilever, the moment is omega L square by 2. It can be seen that a unit strip acts just like a cantilever beam subjected to a uniformly distributed load Qu equal to the net contact pressure. Here you will consider 1 meter strip, as you have seen in the design of slabs. 1 meter strip, unit strip considered for design for in the long direction, similarly in the short direction. So here is a bending moment and the one-way shear formula. Bending formula for the one-way moment, one-way slab moment, omega L square by 2, that is the L, that is L minus C1 divided by 2L. So omega Q U into L square by 2. Bending moment in shorter direction, same way QU into L square by 2, and the maximum one-way shear for flexure. So location should be at distance D. So you can get L minus C1 by 2, okay, or you can say L by 2 minus C1 by 2 at minus D to get at location D distance. Okay, so to get at location D distance, okay, L minus C1 by 2, so you will get this length only, and then minus at the D, so you will get this location for one-way shear. Okay, now transfer of load from column to footing. The concentrated load in the column is to be transferred to the footing by direct bearing of the column over the footing, producing bearing stresses at the interface and by forces in the dowels or column main steel bars that across the joint. What it's saying, from the columns that are steel bars are present, and the load from steel bars transferred to the footing. So when the load transferred to the footing, there is an option that either dowel bars are required in the footing or not for the safe transferring of load from columns to the footing. The loaded area or the area of cross section of the column is to be denoted by A1, whereas a larger area of footing may be considered effective in resisting the bearing stresses and is denoted by A2. The area A2 at certain depth inside the footing is found by spreading the A1 at a slope of lesser 2 horizontal to 1 vertical. So let me take the pen. So when the load from column when the load from the column transferred into the foundation, then it transferred with the slope 2 horizontal 1 vertical. So after that, this area that is A2, that is taking the part in the actual bearing. The concrete present in the larger area A2 around the loaded area around the A1 is the area of cross section of column, lateral confinement to the concrete and causes increase in bearing strength. So if this much area is present around the column, so it will help in increase the bearing strength of the concrete. The increase in the bearing strength is considered equal to under root A2 by A1 whatsoever the value, with a maximum value of 2, means whatsoever the ratio will come, you can take the maximum value of 2. The bearing strength phi Pn is thus estimated by using the following expression: phi Pn equal to 0.85 Fc prime A1 under root A2 by A1, that maximum value can be used as 2. Okay, so less than or equal to 2 means here is the formula, where Fc prime is the slender strength of the concrete. of the footing concrete. The above expression is used to check the concrete in the footing just below the column without dowels having development length beyond this region. Means without dowels, is it okay your footing size, or you need to provide the dowels? And if this capacity, here I will explain. Let me take the pointer. Excess force, if there is a applied load whatsoever coming from the column, minus 5 pn, that is the resistance by the bearing pressure of the soil of the pad here by the A2, if applied, minus this bearing is equal to 0, means there is no need to provide the dowels. And if there is some value, means 5 kilonewton, 6 kilonewton, whatsoever, so you must provide the dowels to resist that load. Okay, area of steel required for dowels, Pu minus 5Pn whatsoever the load divided by 5Y, you will get the area of steel. ACI recommend that if there is no need of dowel, but you must provide the dowels. ACI minimum area of steel required for dowels, that is 0.005 Ag, where Ag is the gross cross section of the supporting member. Okay. The above check and the amount of dowels is required to make sure that the footing concrete is capable of taking the full load of the column. So dowel check we also perform when we do the example. However, if some of the column steel is discontinued at top of the footing, the portion of the column just above the footing will be lacking full development bars. Means here, let me show in the here from the where column and the footing is making a joint, your dowel bars, these are dowel bars, L shape. Okay, so these bars should be extended up to that extent that it producing the proper development. Okay, the bearing strength of this bottom portion of the column is to be checked. The continuing steel must provide a dowel steel area to develop a force equal to whatsoever the value, Pu minus 5Pn. Okay, so here column, again the same that I have discussed in the previous slide. ACI 15.8.2.1 requires that cast in place column and pedestals area of reinforcement across interface must not be less than, means at least must be the 0.005 Ag area of steel for dowels must be provided. Okay, that is the development length for the dowels. You must properly development and properly spliced. Distribution of footing steel. Okay, so in the if there is a square footing, so the same steel will be in the both sides, but if there is a rectangular footing, means one side is longer and the other side is shorter, so then there is some criteria. Distribution of footing steel. The steel bars required along the longer side of the footing, means, let me take the pencil. Okay, here is a longer side, here is a shorter side. So along the longer side, like this longitudinal bars, you will provide as it is. Okay, in the examples definitely I will calculate and provide the reinforcement, and it will clearly show same way. Okay, properly distribute. However, the reinforcement in the longer direction it is provided uniformly, but in the shorter direction, so at where the column is present, that at lesser thickness steel is provided, and away from that the same at larger distance spacing of bars are provided. And in that band where the spacing is less, so here is the criteria. The ratio of reinforcement to be placed the ratio of reinforcement to be placed in the central band with respect to total required reinforcements is taken equal to 2 times 2 by beta plus 1, where beta is the ratio of long to short side of footing. If that is long to short side is 1, so 2 by 2 will be cancelled, same steel will be provided. The remainder of the reinforcement is to be uniformly distributed outside the central band of the reinforcement. Then where in the short side, after the central band at the rest, that spacing will be provided as it is. Now I will start the example 9.1. Here is a statement. So in the slides also present the example, but I will try to cover the example through the book. So let's go with the book. So I will read the statement and perform the example.